And welcome. Please, it's now 23 years since I left Glasgow University, but I still have very fond memories, and I'm still quite feel very attached to the department and talk with members of the department quite regularly. So it's rather a joy to be back with you, albeit virtually at the moment. So this is a technical talk about hashing expression trees, but I think we'll sort of segue towards the end into more general discussion. So if you've got questions about anything to do with Haskell or GHC or me or Microsoft and so forth, then you'll feel free to sort of save those up and ask them all later, and we can turn into a more general discussion. I think the slot for this conversation is about an hour and a half. It would be enjoyable for me if you feel able to put your camera on. Then I'm not just speaking to a blank screen, but to some actual live, breathing human beings. It's a lot more rewarding as a speaker, I tell you. I don't know whether you've ever tried this, but a load of black icons is less fun. So what else to say? Yes. Please do ask questions or make comments during the talk. It's more fun, again, for me to feel that it helps me to feel that you're engaged. It also helps to give me some feedback. Usually as a speaker, you can see if the audience has their attention drifting, or if they're reading their email, or are somehow becoming disengaged, and take countermeasures. But I can't see that. So do me the honor of just asking a question if you get lost or confused, because I'd much rather shorten the talk but still have you all on board than rabbit on when all of you have sort of lost interest or lost engagement. Because once you get completely lost in a talk, it's much less fun. You tend to do something else. So please do that. I will keep an eye on the sort of hands up thing, but you can just switch your sound on and break in and interrupt me, and we'll have a conversation about any questions or observations you might have anyway. Okay, all good. Fine. So I have let's see, I have 20 participants and about 5 cameras. You can do better than that. So here's the subject of the talk. How are we to find all equal sub-expressions in some kind of expression tree or program term? So here in this little program, I've got f of x equals g of x plus 1, x plus 1. I'd like to somehow common up that x plus 1 and have a let binding that binds t to x plus 1 and then says ftt. So this is a very standard standard question, and it comes up in every compiler book. It's usually called common sub-expression. But you might also use something similar to say, oh, I'd like to save storage in representing this expression tree, perhaps by representing common sub-expressions once rather than by representing them many times. So even the first expression might be represented by g. The 2 arguments to g might be pointers to the same thing, right? Even without a let expression. So and yet another application is in a particular form of compiler optimization called equality saturation. Then you want to find equal subtrees rather aggressively. So that's the general setup that we want to do. And one other piece about the general setup is I'd like to do this in an incremental way. So the batch way is to say, here's an expression, find all the common sub-expressions. A slightly more challenging task is to do that to begin with, and then as we rewrite the expression, perhaps one little rewrite at a time in different parts of the expression tree, I'd like to maintain my analysis of all equivalent sub-expressions, right? Rather than rerunning the batch process every time, I might hope to make a small change in the part of the expression tree that I change, a sort of an incremental algorithm, if you like. So that's the challenge. That's the task, right? Now, one obvious way to do this task that everybody's heard about is hash consing, and there the idea is that every node in the tree has some kind of hash value, and when you're building a new node, presumably by combining existing nodes together, we compute the hash of the new node from the hashes already computed of each children. So every node has an extra field, which is its hash. I'm in the middle of something at the moment, Ken's. My my 10-year-old boy who is programming Scratch. every node has a field for its hash code. When we want to make a new node, we combine the hashes of its children together with, say, in this case, it's a plus operation to combine with that, and then we can make a hash code for the new tree. And this is a very nice incremental bottom-up algorithm, right? So if I find a hit, I can reuse the existing node. I have to be careful about checking whether it's a false hit because two different nodes have mapped to the same hash code. But apart from that, I can rapidly find my way to an existing node if it already exists. And if I get a miss, then I allocate a new node in the hash table, and there we go. So you can regard this as a kind of memorization process. You're memorizing the node constructor function itself. And you'll notice that this is by design incremental, that if I rewrite a small piece of the tree, then I'm allocating a few new nodes, and I can simply construct their hash codes from the hash codes of their children, and none of the hash codes of any of the other parts of the tree that hasn't been changed are affected. Everything's easy. Somebody said GTT, surely, and it was indeed, yes, in my first slide. There is a typo. Thank you, Gale or Gales. That should be GTT in this slide. Thank you. Okay, that's hash consing. So hash consing looks as if all good. What's the problem? Well, problem is lambda, of course. So lambda is the good thing about expression trees. It's also the difficult thing. So in these two lambda terms, here's two definitions for f and g. And in these two lambda terms, each of them has a subexpression x plus 1. Are these two the same? What do you think? I mean, for structure showing, if I'm just trying to save storage space, then yes, I could represent each of those x plus 1s by a pointer to the same x plus 1 subtree. But semantically, of course, they're completely different. I mean, I couldn't do common subexpression on this and say let t equal x plus 1 and then say lambda x g of t, right? That would be obvious nonsense. So here we can see that for depending on the exact notion of what we mean by equivalent, we might want to treat these two subexpressions as equal or not. So there you go. One way to avoid this sort of false positive here is to make every binder unique. Now, of course, that's a bit of work to maintain, because now you have to make sure every time you allocate a fresh lambda that you choose a binder that is not already in use anywhere in the expression tree you have. That's mildly painful, but maybe we could do that, and then at least we wouldn't get these false positives. That's not the only problem of lambdas, but this solves one of those problems with lambdas. So far, so good. Any observations or questions?
What if g is times 2 itself?
What if g is what?
Is the function that multiplies by 2.
This particular g isn't. It's the function that adds 1 and multiplies by 2. Do you mean if there's another g?
Well, if g were defined as being times 2, then the two expressions would look even more similar.
Oh, you mean because the top one might look like x plus 1 times 2?
Yes.
Yes, it might. But if the top expression looked like x plus 1 times 2, or lambda x plus 1 times 2, and the bottom one looked like lambda x plus 1 times 2, then they really would be the same.
Yes.
And that would be fine. Then you could common up the entire lambda.
Yeah.
Right?
But now if you give each one a unique identifier to say that x is different from y.
Very good. Yes, right. So let's see, I'm going to come to false negatives in a second. That would be if I then had lambda x plus 1 times 2 and lambda y plus 1 times 2, they kind of look different. They would be hashed to different things, but they actually want them to be the same. Yes. So that's a false negative. So you're right on the money. We've avoided false positives by making all the binders unique, but we've increased the number of false negatives. And we don't really want any false positives or any false negatives. Good. Anyone else? Okay, then let's see. Right, in fact, that's exactly the point made in this slide here. So here I've got another example with a different f and g, in which there's two sub-expressions, lambda x plus 1, lambda y plus 1, and we'd like to common those up. But in order to common them up, we have to represent the fact that lambda x plus 1 and lambda y plus 1 are equivalent, but they don't have the same hash code. right? And so that'll be a false negative. So that's bad. Let's see, why don't they have the same hash code? Well, because the subtrees, the subtree X and the subtree Y must have different subcodes. We couldn't make every variable have the same hash code. So, and then once you've got the the X and the Y with different hash codes, then you're lost all the way up, right? Because now I'm going to put a lambda on the front, have two expressions with different hash codes. Bad, 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 bad. So our problem really is that I can't really compute the hash of lambda x plus 1 from the hash of x plus 1. So hashing is somehow not compositional, at least not if we want to respect alpha equivalence. Do you see the problem?
So then the obvious question is, what about the Brown indices?
Very good question. Yes, as Andrew asked, why don't we just use De Bruijn indices instead? Well, so just to quick revision for anybody who's not come across De Bruijn indices before. So De Bruijn indexing, there's kind of two more or less equivalent ways to do it. So here I'm taking it as being that you remove the variable names altogether. So instead of at the top, we got lambda x, lambda y, x times y plus x, but at the bottom, I've got lambda, lambda, right? So the lambdas carry no name, but instead at a variable occurrence site, like where I did have x, I'm going to have hash 1. And what does hash 1 mean? It means the variable bound by the lambda that's one level out. And hash 0 means the variable bound by the immediately enclosing lambda. So I hope you can see that x is the variable bound by the lambda one level out, and y is the variable bound by the immediate lambda. So the body here turns into hash 1 plus hash 0 times hash 1. Okay, so now the result is that we don't have any since we don't have any of these variables x and y, right, that are sort of have these arbitrary names, they in effect, a lambda has a canonical name, right? Lambda x plus 1, lambda y plus 1 both have a canonical representation as lambda dot hash 0 plus 1, right? There's only one hash code for that. So miraculously, lambda x plus 1, lambda y plus 1 represented the same way, have the same hash code, will get common sub-expressioned. And job done. So as Andrew implies, couldn't we just use De Bruijn indices instead, and then we could go home and not have this talk? Sadly, not. And here's why. Firstly, using De Bruijn indices in your expression trees has global implications. This isn't just a local decision you can make in one part of your compiler. It pervasively affects the rest of your compiler. For example, when you perform substitution, a relatively straightforward operation usually, you end up having to do a lot of index readjustment. And there's quite a lot of papers about this. You can find dozens of papers in the literature about various ways of using De Bruijn-like notations and trying to deal with the efficiency problems of the index adjustment you have to do in order to keep all the De Bruijn indices right, especially under substitution. But my main point here is just we were trying to do just a little local thing, right? Find common sub-expressions, and we found that it had a global impact across our entire compiler. So that might be something we want, but it might not. Even worse, though, even from the narrow point of view of this particular problem, using De Bruijn indices suffers from both false positives and false negatives, and it's not obvious. So here's the false negatives. Here's a example. There's a lambda t, then there's a f applied to lambda x plus t, and a lambda y, lambda x plus t. Now, those lambda x plus t's, those are the same thing, right? Those are equivalent. They should definitely be let bound, right? We could let bind it to a function called h. But in De Bruijn notation, the x in the right-hand lambda is bound. The t in the right-hand lambda is bound 2 levels out, and the t in the left-hand lambda is only bound 1 level out. Okay, so these two look different, even though they should be the same. This is a false negative. That's not good. But it also suffers from false positives. So here's the same lambda t. Now I've got lambda x t times x. And then my second argument here is lambda x y times x. Well, the lambda x t times x is the goes lambda #1, one level out, that's the t, plus #0, the innermost one. But alas, the lambda x y times x is also lambda #1, that's the x, one level out, and #0. Do you see the problem? So false positives and false negatives, not great. So so it seems that using De Bruijn indices is not isn't a quick win. Doesn't just solve our problem. Okay. You could try doing it the other way around, numbering from the outside rather than the inside, and that has problems of its own, and I shan't go through those. So our summary so far is that for this apparently simple problem, I thought, look, the literature is bound to contain lots of well worked out algorithms for doing this problem. We couldn't find any. I don't think there's an efficient compositional algorithm in the literature. That's the problem we're going to address. So Uma asked, does this happen with De Bruijn levels too? So yes, that's what I meant by numbering from outside in versus inside out. And that certainly suffers a lot from this index readjustment problem. Every time you wrap something in a lambda, you have to go around adjusting everything. That's really painful. But also you get false negatives as well. Things that should be the same look different. I think I got that right. Yes, if you think that's wrong, then let's come back to that a little later. But I believe that it suffers from both false positives and false negatives. It may be that it's only false negatives. I don't think it's an easy win, but noodle on it a bit while I'm speaking. I should have a categorical answer to that question. I don't immediately. Anyone else got any observations at this point? Because I'm now about to start on the sort of sequence that leads us to the story that we do have. Kai Oliver, are you about to say something? I see yellow boxes. Maybe not. Okay. Feel free to use sound, by the way. You can type stuff in the chat as well, but sound waves are also good. Oh, Gale has a example, which can everybody see the chat? Yes, everybody can see the chat. So you can see Gale's example, which it says is using level numbers means a variable is replaced by the identity of the lambda that binds it, counting from the outside. So #0 would mean the lambda bound by would mean the bounder. #0 means the variable bound by the outermost lambda. #1 means the variable bound by the next to outermost lambda. #2 means the variable bound by the next to outermost lambda, and so forth. And so Gale's helpfully posted an example in which there's a it's got a lambda y.y and a lambda x.x. And they should both be very good. They should both be identical, right? They should be common sub-expressionable. They're both the identity function, but using level numbers, they look different. One's lambda 1.1, the other's, well, the other was, one is lambda.1 and the other is lambda.0. Yeah, thanks. Good example. Anybody else? Cool. Okay, so let me tell you what our approach to solving this problem is. So here it is. It's going to take it in two steps. First, from any expression, I'm going to describe how to build what we call an e-summary. And it's going to turn out that an e-summary can be computed in a compositional way. The e-summary for a node can be computed from the e-summary of its children. And two nodes are equivalent, alpha equivalent, if and only if they have the same e-summary, for some notion of same. And moreover, but an e-summary is not information losing. Unlike hashing, e-summaries are not information losing. I can convert from an expression to an e-summary, and from an e-summary back to an expression, to an equivalent expression, at least an alpha equivalent expression. That's step one, to make this e-summary thing. Step two is then to define a hashing function for e-summaries, so that the hash of the e-summary for a node can be computed from the hash of the e-summaries of its children. And then if two nodes have different hash codes, well, they're definitely not equivalent. And if they have the same hash code, they might be equivalent. And we, as usual, in any hashing scheme, have to do the after the fact check to say, is this a false hit in the hash table? Okay, so 2 steps. From an expression, derive its e-summary. From the e-summary, hash it. That's the information losing step. Okay. So what's an e-summary? An e-summary is a pair of a structure and a free variable map. So for the expression x plus y times x, the structure is spot plus spot times spot. So by structure, I mean remove all the variables and just replace them with spot, and otherwise keep everything, right? So remember, it was the variables that caused the trouble. So aside from variables, hash consing was perfectly fine. So the structure part is designed to be cool for hash consing, okay? But then we need to keep something else so that we can, we can't map every expression to spot. If it was x plus y times y, that would also have structure spot plus spot times spot. We have to need something to keep them apart. So we're going to have a free variable map that maps a variable to its position tree. So its position tree is a little data structure that describes all of the places where that variable occurs. If it doesn't occur anywhere, well, it won't be in the free variable map. Okay, so here I've got a little, my structure map is mapping y to, what's this, p right? That suggests that it's in the right-hand subtree of the root node, and sure enough it is, the right-hand argument of the plus. Then I have to go left, but it's the left-hand argument of times, and then, well, that's where y is, so that's why I say p right of p left of p here, right? That's like a little path that tells you turn left, turn right, and now you've got it, right? You should have found your way to a spot, and that spot is y spot. Now x occurs twice, so it occurs in both subtrees of the plus node, hence p both. And in the left subtree, the first argument of p both, it says p here, that, spot, there's x right here. And in the other subtree, it's in the right-hand branch. Okay, so have you got the idea about this at first doesn't look like an advantage. It looks like the representation of an e-summary might be, bigger than the expression it describes. And so it might, but never mind. It's we've just peeled the expression apart into its structure with nothing about variables, and its variables without very much about structure. Okay. So then when we come to a lambda, we're going to stick in a lambda the position tree that describes the places where that binder can occur, that binder occurs. So while y was a free variable on this slide, right, then y is in the free variable map. When I move outside a lambda, then I put in the lambda node, I put the position tree of y. And then in the free variable map, I remove y from the free variable map, leaving only the free variable map for x. Okay. I'm hoping this is, so please speak now if you're getting lost.
So this is purely based on the name at this point, right? You look up the name in the free variable map, take
Yes, that's right,
and stick it in the lambda.
Because my starting point is a tree with named lambdas in it.
Yep.
Right. Yeah. So here we are, the bit in the sort of where it says lambda contains position tree, the bit of code under there is the starting point. And so, yes, we look up y. So indeed, the free variable map also mentions names, right? It's it definitely mentions names, the names of the free variables, right? Which are still have names. Yeah. There we are. So here's a little picture to show that kind of evolution happening. So here's on the left is a lambda term. It's not quite the same lambda term that I've had so far. In fact, it's a rather funny lambda term because it's got a multiplication there with the lambda on the left, but never mind. It's just some constructor at the top, which combines a lambda. Maybe it's apply instead of multiplication. Yes, in fact, as a term at the bottom, it is just apply. So then what are we going to do for that multiply node at the bottom? The structure is just multiply spot spot, and the var map gives you a position tree for b and a position tree for x. When I move outside the lambda b, I've stuck in the lambda, I put the position tree for B, and in the var map, I have left the binding for X, the position tree for X. Then when I come to this apply node or multiply node, whatever it is, I have to augment the position tree for X because it occurs in both subtrees. And then when I come across the lambda, I stick in the position tree for X, and now I've got an empty var map. Okay, that's the idea. So with rather less arm waving, this is what it would look like in Haskell. Let's say expressions are just variables, applications, and lambdas. And the name here might be something like a string or a number, who knows. So that's my source expression. And then, so this if a name is just a string, then lambda x plus x is going to be represented by this application tree here. And here I've got plus I've been previously been regarding as a constant, and here it's turned into something like a variable, but I'm going to ignore that. So here's what an e-summary might look like. An e-summary is just a pair of a structure and a var map. Remember, what is a structure? Well, it's this everything except the variables thing. So it's either svar, that's spot previously, or it's sapp, that's the branching thing, or it's an slam. And then what does the slam got to contain? Well, you remember that lambdas, in this slide, lambdas have as their binder a position tree that describes the places where the bound variable occurs. So when I come to the data type, I need a pos tree, a position tree, and it has to be a maybe pos tree because, anybody care to say?
You might declare a constant function. So
yes, a function that does not mention its free variables, sorry, does not mention its bound variable. What pos tree can I put there? Well, I could have augmented the pos tree type with empty, but this emptiness can never occur at a leaf of the pos tree type, so it's convenient to put it just at the root by using a maybe here. And what's a pos tree? Well, you've seen it already. Either says go left, go right, go to both ways, and then a p here to say here's the spot. A var map is just a finite mapping from names to pos trees, and this maybe thing is just an optional A. Okay. Any questions at this point or observations? I'm hoping that this has sort of turned my sort of slightly arm wavy description into something very tangible and concrete. Just to respond to Uma, you have to explain to me what are code De Bruijn indices? I've never heard of them. Can you switch your microphone on and tell us? I can see you've unmuted yourself, but I can't hear you.
Yeah, sorry.
Now I can, yeah.
From what I understand, it's something somewhat similar where you say in unbinding whether something goes right or left in the expression where the binding occurs.
Okay, maybe this is something piece of related work I don't know about, which would be very helpful. So if people can go off and Google code De Bruijn indices while I'm speaking, you can maybe fill me in later. That's good. Thank you. Anyone else? Okay, so here's a function that builds an e-summary from an expression. It's pretty simple, right? So summarize takes an expression and returns an e-summary. On a variable, it returns, well, what? The structure is just svar, meaning spot, and the variable map is a unit mapping from the variable name to p here. For a lambda, I've got to look up the variable in the map. So this is exactly what I think Christian was mentioning. Look it up, stick that in the slam node, and then I must remember to delete the variable from the variable map that comes back from summarize. And for applications, you can see that it's not going to be too hard. I'm somehow going to combine the e-summaries from E1 and E2. It's not very hard to do that combination. I think I'm not writing out the code here. But notice that they don't lose information, right? I can equally write a function that takes an e-summary, we'll call it rebuild, that takes an e-summary and gives you an expression. And the code for that function is given in the paper that accompanies this talk. So at the moment, I haven't lost any information. You might wonder about the name of the variable. Can I reconstruct exactly the original expression, complete with its name, the name of the lambda? To do that, I would probably have to record in this slam node of the structure, I'd have to record the name of the bound variable only in order to be able to reconstruct the original lambda. But in fact, we are never going to construct the original lambda, so I've left it out. But I just want to point out to you that we can even go as far as reconstructing precisely the original one rather than something that's simply alpha equivalent to the original by adding a little bit more information. It's very, very easy to do. Okay. So next question then is, if all I've done is convert expressions from one representation to another, why have I bothered? Well, and it's because I can construct hash codes for the e-summaries, right? In fact, I can hash e-summaries in a compositional way, whereas I cannot hash expressions in a compositional way for reasons we've discussed in the first part of the talk. So how can we hash e-summaries in a compositional way? Well, given an e-summary, here's a function that takes an e-summary and gives its hash code. Giving an e-summary, which is a pair of a structure and a variable map, maybe I could just hash the structure and hash the variable map and then take those two hashes and squash them together with a hash function. So it doesn't seem too hard. Could that be fast? Could that be a constant time operation? It depends what hash structure and hash var map do. Well, let's start off with hash structure. Now, I mentioned to you that structures are designed to be hash consable. They don't have variables in them. So hash consing works perfectly fine for structures. Right? I can just say every structure I'll give a hash code. Whenever I'm building a new structure, I'm combining two existing structures. So I'll look at the hash codes of its children and all of that. Very simple. Look at this pos tree type, that's all that's in it. And the structure type, there's no variables. It's completely straightforward. So sort of nod if you think that's straightforward. I'm looking. I've got 3 out of 5 nodding. Craig, you're not nodding. But thumbs up will do. Yes, all right. Thank you. Okay, so structure part, pretty easy. Excuse me. In fact, we can go a little bit further. We don't even need to keep the original structure at all. Rather than making a, let's see, at the moment our e-summary was, well, it was a pair of a structure and a var map. Our hashed e-summary can be a pair of a structure hash, and well, we haven't quite worked out what a hash var map is, but we don't ever need to build the structure and then hash it. We simply build its hash code, right? So we do not build a tree and construct its hash code. We simply only hang on to the hash codes. That's quite an important point, right? It's quite a simple point, but it's important. The structures themselves, that little data structure here, structures and pos trees, right? We never ever allocate any of them in this process because we can just work with the hash codes alone. Does that make sense? There was simply an intellectual stepping stone to get us to the idea of structure hash. So I've written out some code here, right, that if I was calling, if I'm trying to write a function that takes an expression and delivers an H summary, a hash summary, well then for a variable node, I'd just compute hash of svar. And for a lambda node, I compute hash of slam and that lookup thing and the underlying structure hash for the body, right? So I hope you're looking at this code and thinking, of course, at least for the first component of H summary, the structure hash, it's plain that we can simply build the hash codes of the structures and never build the structures. Remember that if we get a hash collision, because two expressions yield an H summary with the same hash code, we still, as in every hashing algorithm, have to say, oh, more than one thing has fallen into the same hash bucket, and then I'm just going to fall back on ordinary old equality comparison respecting alpha on the expressions themselves, the original expressions, which I have in hand. Right.
And I imagine because you can reconstruct the E summary from its hash, if you do get a collision, you can just recompute the entire path.
No, I cannot construct a summary. I cannot construct a structure from a structure hash.
Well, okay, if the particular hash code has collisions,
Yeah.
then that's a problem.
Yeah.
But is it also a problem for a hash without collisions?
Oh, maybe without collisions you could reconstruct, but we may have collisions, right?
Yep. Well,
it would be very fragile if we said everything will work fine until you had collisions, right? No hashing algorithm could survive that. No. So, but we're never going to need to, right? We never need to. Our e-summaries, I wanted to point out, you can be interconvertible with expressions, but our only goal is to say, find me all the equivalent expressions, as it were, find me a hash code for an expression in a compositional, fast and compositional way, which allows me to say, well, I think this expression is the same as this other one, but you still need to do an equality comparison just to check that I haven't got a false positive. Every hashing algorithm is subject to false positives. Okay, so I think I'm done with the hashing for the structure part. We now need to talk about hashing for the variable map part. Anybody else got any questions or observations about hashing for the structure part? Now, let me look in the chat there, because you're using chat but not sound. Okay, so we got a link that I won't look at now to code De Broglie indices. Thank you very much. And GitHub repository. Is delete map applying some magic to the keys that are not getting deleted to mark that we've gone under a binder? No, it is not. No. If I look back at my examples, let's see. Here, I've got a variable map in which I've got both x and y. And when I go outside the lambda y, I look up the y, and find that it's bound to p right to p left to p here. So I put that in the lambda, but then the free variable map that I get out is completely unadjusted, right? It's got y deleted, but nothing has changed about x, because I don't have to record. You could put a p lam, I suppose, in that pository, but there's no need to, because lambdas have a unique child. So there's no need to say, do I go left or right? Or both, right? So there's no need to put anything in the pository when you go past the lambda. So yeah, no need to mess with x. Okay, Calais, is that fine? Okay, I see him nod. That's great. Thank you. Anybody else? Okay, let's see. So now I want to, before talking about hashing the variable map part, I just want to point out two things that you've all been thinking about, but have very politely not said, which is that looks as if there's a sort of serious problem with app nodes. So look, here's an example in which I've got the app node at the top has a subtree x, which has its own variable map, and a subtree app yx, which has its own variable map. And then when I combine them, I only got to say x goes to p both because it occurs in both branches, and y is a p right of a p left. I've got to modify y's binding. So I need to visit every binding of both maps, right, when I combine them. I can't just zip the maps together. I've actually got to modify the bindings, right? So when I go at every app node, then it's as if I've got to do something to every entry in the variable maps. Now, that's not so bad in a balanced tree case, but if it was a very unbalanced expression, an expression of size n, which was very unbalanced, right, but each time added a new variable, say, then at every step of the tree, or even if it didn't add a variable, if there was an x in the corner, then at the bottom level, it would say x maps to p right. At the next level, it would say X maps to Y. Oh no, it helps if I add a variable each time. I'd have to add X and Y. At the next level, I've had X, Y, and Z. At the next level, I have X, Y, Z, and P. And at every level, I'm looking at all of the bindings in the variable map for all of the free variables. And at each level, I get one more free variable and I have to process all their bindings again. So this is quadratic.
So every subtree contains its own map, and
Yes.
you could index that by the name as well, right? So you've got the map of free variables.
Yes.
And so when Y occurred in the right, that gets removed from the projection that the outermost app sees. So then the recomputing the paths for everything in the lower trees is just a projection and adding a prefix.
Well, hang on, remember I'm computing these maps in a sort of bottom-up way when I do my summarization, right?
Yep.
So imagine you're at the bottom of this picture with Y and X. You've got a map, a finite map that maps Y to P here, and one that maps X to P here.
Yep.
And I have to cough up a finite map that maps X to P right of P here and Y to P left of P here.
Yeah. And so when you go up a level, you look, the map is already sort of linear because it's a map, right? You just traverse all the names in
Yes,
sequence.
that's right. So I need to look at, but I need to build a completely new map, right?
Yep.
And at the next level up, I need to build another completely new map.
Yes.
And if at each level, the map is one bigger than before, then the build a completely new map task takes cost, order, size of the map.
Yes.
And so at every level of the tree, at every one of n levels, I have to do work of size order n.
Yeah.
Well,
unless
order 1, then order
you're
2, then
lazy
order 3.
about it and sort of rather than immediately add the prefix to every content, every item in the map, you keep a sort of linked list of the previous maps and say for each one, do this work at the end.
Yes, then you'd be forced to sort of do some kind of lookup, because when you did a lookup to say where is Y used, you'd end up having to
then you pay the cost.
Yeah.
Yep.
So I think if you nail down the carpet in one place, it'll pop up somewhere else.
Yeah.
So maybe you can do better. So this is also in the nature of a challenge, right? Nobody's really tried to do this before, as far as I can tell. I'm going to describe a solution that we think works reasonably well, but you may be able to come up with a better one. So, I'm talking to 20 odd very smart people doing PhDs. Maybe you can do this in your spare time. And it's a nice problem because it's very easy to describe, and I think comparatively understudied. And maybe we don't have the best solution. So anyway, anything that goes quadratic is bad, right? N log n is kind of acceptable because log n, even for very big numbers, log n is pretty small, but n squared, not good. So let's see. So that's problem number one. So the idea for solving problem number one is to the problem with a very unbalanced map is that very unbalanced trees is that we have a big subtree on one side with a lot of bindings in it and a little subtree on the other side with very few bindings in it. Could we arrange that we only do work proportional to the size of the smaller subtree? At least the smaller variable map. Right. So if the left-hand side is size 1,000 and the right-hand side is size 2, then do work, order 2 rather than order 1,000. Right. That's the idea. So, and morally, that means what we want to do is to leave one map alone somehow and modify the other. Right. So, as it were, could we leave the could we somehow leave the bindings at least for Y, which doesn't appear on the left, right? Imagine that on the right, on the left-hand side in this picture, I've got a use of X bound to P here. On the right-hand side, imagine that was a huge tree with 100 free variables, including X, but also including lots of free variables, not X. Could we leave the bindings for all of those unchanged and just somehow modify the binding for X? Right. So instead of reconstructing a wholly new finite map, we take the bigger of the finite maps and modify it in a few places. That's the idea. So, so what I'd like then, so so Y here in this picture is a poster child for all of the free variables that do not occur on the left. And I want to leave its bindings unchanged. So now in the green bit at the top, you can see Y is still bound to P left to P here, right? Unchanged from the right, even though I've gone one level up, right? But I don't want to mess with all of those because there's Y1, there's Y2, there's Y3, there's Y4. Leave all of them alone. The binding for X I'm willing to modify, but it's coming from the small subtree and there's only a few of them. That's the intuition here, okay? But now I need to, we appear to have lost information because somehow, how would I know that Y only occurs in the right? Yeah.
I don't want to jump the gun, but does this have something to do with function composition, where you compose the lambda, the locators for the lambdas, and then you get a single lambda being the composition of?
No, I don't think so.
lambdas?
That doesn't ring any bells. I'll show you what we do have in mind, and then you can say if it's what you meant.
Okay.
Anyone else at this point? Okay, so we seem to have lost information, but maybe we can record the extra information where? Where would be a good place to record it? In the structure, right, which is the other component of our tree, right? So maybe in the structure, we can record a clue, some breadcrumbs that tell us what we did with the variable maps. So firstly, I've got this bigger map thing that's a simple Boolean flag that said which side had the bigger map, right? So in my, so here in the app node at the top, in the sapp, remember sapp is the bit of the structure that corresponds to app in the original tree. In the sapp node, I'm going to record here that it was the right subtree that was the bigger one, and the left subtree was the smaller one. So that's one piece of information. It's easy to record. It still means that structures are perfectly hashable. Then what's the other thing I'm going to record? I'm going to record a depth flag that says how deep, or it says the depth of the deepest subtree rooted here. All right, you'll see why that occurs in just a second, but at least you can see that it's simple and compositional. So if I've got an app node, the depth of the app node is one bigger than the deeper of the two children. Right, so a pretty simple thing to do. I'll show you why we need it in a second. So then in the pos tree, now what am I going to record? I'm going to record a, I'm going to get rid of the P left and P right altogether. In fact, I'm only going to have P both. Because for P left and P right, that's going to say well, you'll see. And for P both, I'm going to record the depth at which this P both is relevant and the two child pos trees. One of which is a maybe for exactly the same reason that the pos tree in a lambda is a maybe. So this is the only tricky bit of this talk, is getting this bit of structure right. So let me give you the example here then. So every node, first in red, attached to every node, I put its depth, y and 0 at depth, so y and x at the bottom of depth 0. The app above them is of depth 1. The x node on the left is of depth 0. The app node at the top is 1 plus the bigger of its children. Its children are 0 and 1, so it's 1 bigger than 1, so its depth is 2, okay? So, and I've also written on here the smaller, bigger in red is the meant to be those bigger map flags, right? In fact, on the bottommost app node, I've just arbitrarily chosen the left one to be treated as smaller. They're both the same size, but we have to choose. Now, now let's see. So what happened at the bottom? Look, focus on the bottommost app node. its children said X maps to P here, Y maps to P here, then, but when I go up a level, remember the bigger map is unchanged. So X still maps to P here. It was described to be the bigger map. Well, they were equal, but we chose the right-hand one to be the bigger one. So the X maps to P here is staying unchanged, but I'm going to modify the bindings that come from the left-hand child, right? The smaller map. So Y here is going to map to a P both at depth 1, because the 1 is the depth of this app, and the nothing says Y does not occur in the other subtree, right? The P here comes directly, when I said Y maps to P both of 1, nothing, P here, the P here in that case comes from the left-hand child. Okay. So that was a little bit like a P left, right? That P both of 1, nothing, that was a bit like a P left, but it was only a P left because it was in combination with that smaller and bigger flag that told you whether it was left or right. Okay. Now go up one more level to the app node at the top. So here, the bigger map comes from the right. So we're going to leave those X and Y bindings unchanged and instead adjust the bindings for everything coming from the left. What's coming from the left? From the left is coming X maps to P here. So what am I going to do now? Well, the binding for Y, you can see in the green box at the top, the binding for Y remains completely unchanged because it doesn't occur on the left. The binding for X does change because it occurs on the left, and it changes to a P both at level 2 because this is a level 2 app. And now that just P here says, oh, it did occur in the bigger subtree, and here's the pos tree for it, right? So I hope that's given you sort of enough clues that you could probably write the thing that builds the e-summary from an expression without very much difficulty. And in doing so, at an app node, you would take the variable map from the right-hand, from the bigger side. You would take the variable map from the smaller side, turn it into a list, and then for each binding in the variable map from the smaller side, you would modify the variable map from the bigger side. And that is turns out to be an n log squared n operation altogether. Oh, that's perfectly fine. Okay.
I'm a bit confused why at the end of the Y in the green map is P here. Should it not be the Y that's in the bigger the tree? So P both 1, nothing, P both 1, nothing, P here.
No, the reason is that in the remember, our goal is at the topmost app node, we want to take the bigger map and leave it completely unchanged, except alter the entries for the variables in the smaller map. Well, Y is not in the smaller map on the left. So the entry for Y must be precisely identical to the one in the sort of orange colored map halfway down the slide. Right. So we're not going to change those entries. Our idea is from the bigger map, we're going to leave them all the same, but we're going to take the entries in the smaller map and modify those entries only in the bigger map.
So when stepping into the larger subtree, you don't change the variable map at all?
In stepping into the larger subtree, you do not change the, well, actually you have to be a little bit careful. In stepping into the larger subtree, if you imagine now going inwards, starting with the green map, we've got 2 P both nodes, haven't we? This is why the level number in the P both is important, because we look at P both 1, we say, this is an app at level 2 and a P both at level 1. So it doesn't get changed at all. So when you step inside, push that unchanged into the bigger subtree. But the X maps to P both 2, that says that 2 means it happens right here, this app. So we have to split it. And indeed, you can split it into the orange X maps to P here and the orange X maps to P here in the 2 branches.
Okay, that makes sense. Thanks.
Now, you might wonder, this business about stepping inside and we've got to look at all the things. Well, that could be expensive. But that process is only if you want to reconstruct an expression from an e-summary. It forms no part of the hashing process, as we'll see. So the rebuilding process is mainly an intellectual stepping stone that reassures us that building the e-summary has not lost any information. So the only information losing step is the hashing part, and we can adjust its level of information loss by adjusting the size of the hash table or the cleverness of the hashing function. But we've not lost information to get to the e-summary. So it's helpful to know that rebuild exists, but it does not matter if it's expensive. Okay. Cool. So Andrew says, yes, thank you, Craig, for the question. It was an excellent question. So, and Chris, given the bindings, how do we see which side was the bigger one? Do you want to just use sound waves to, I'm not quite sure what your question means. Can you just ask it again?
Sure. So once we've computed those, what we have in the green box.
Yeah.
And now want to, so how can we now know whether the left or the right branch was bigger, only given that information?
Oh,
or don't we need to go that way?
Oh, remember that when we're going, if you're going down, then you have in your hand a structure and a variable map, right? I'm only showing you the variable map here, but the structure contains these depth flags and the bigger map flag that tells you which side is bigger.
Ah, okay.
Right.
Mm-hmm. Thanks, I forgot that.
Okay. Fine. So, yes. So I think this is a sort of simple complexity argument that argues that the in any tree, the worst case here becomes the since the work done at an app node is proportional to the size of the smaller map. The worst case is when both trees have the same size smaller map. But fortunately, that is of log here's a little complexity argument that says at each level you do twice as much work as work before, but on half as many nodes. So you get an n log n amount of work in total. Okay. The second main idea that I just want to present in this talk, because I'm conscious that we are actually now at 3 o'clock, and so I'm going to try to move towards wrapping up, but I really want to get this one idea across. The second interesting idea in the paper is for hashing variable maps themselves. Remember, I don't really want to carry these variable maps around. I'd rather carry their hash codes around. So how can I get the hash of a variable map? Well, what is an HVAR map? Which is a map for variables to pos trees, but we've agreed that we don't need to keep pos trees. We can keep pos tree hashes. That's fine. But we still look as if we need to keep finite maps of pos tree hashes. And that might be okay, except that I want to have a constant time operation to give me the hash code of a variable map. If a variable map is big, then I could hash together all the variable pos tree hash bindings, but that's order size of the variable map, so that's not so good. So one idea you might think is I could just maintain a triple of the HVAR map, that is this finite mapping from variables to pos tree hashes, and a single hash code, a 64-bit or 128-bit hash code for the whole variable map. And that would be fine when I was extending the variable map, adding to it, but not so fine when I'm deleting from it, right? If I know the single hash code for VM, what's the hash code for, well, if I delete a key from the map? That's not if I've got a hash code is 129 is the hash code for a map. If I delete variable x from hash code 29, what do I get left with? Who knows, right? No way. It's not a compositional operation. So that's a bit of a problem. But one clever way to solve that problem is this: supposing we define the hash of a variable map is the XOR of the hashes of its key value pairs. Remember, a finite mapping is no more than a set of key value pairs. If I take the XOR of the hashes of its key value pairs, well then, that's certainly a hash, and I can delete from that hash code by XORing. I can delete a key value pair by taking the hash of the key value pair and XORing it again, because if you XOR twice, you get 0, right? So now I can compositionally delete. Here's the code, right? I've written it in this little piece of code here. So that's nice and simple. But the obvious question is,
What if you need to add twice the same structure to them?
Oh, well, that's okay, because if you want to add something to a variable map twice, you overwrite the previous entry, right? So you move it and add it. I mean, if I've got a
Yeah.
binding X maps to, if I've got a finite mapping that maps X to some value, and then I add another binding for X to a different value, well, finite maps don't do that. You could say map X to a list of values, but here X always maps to one value. And moreover, we may modify the finite map, which you can model by deleting and then adding. So when we want to modify a map, yes, we will first delete the old entry and then we will add the new entry. So we will XOR the old entry in to delete it and then XOR the new entry in to put it back. Okay?
Yep.
So there is another obvious problem with XORing though. It's not cryptographically strong, right? The point about hashing is you're meant to not get accidental collisions. So like if a hash function mapped everything to 0, a hash code of anything is 0, it's a very fast hash function, but everything collides. So we try to design hash functions quite carefully so that they are unlikely to collide. I'll have to do it a little later. It turns out, though, that doing a bit of mathematics, you can figure out that, in fact, this is not a problem. And I'm not going to describe why now. I'm going to say, look at the paper. So there's an argument in the paper that says this particular issue about getting lots of false collisions by using XOR, which is a dodgy thing to do, won't happen in practice, or statistically extremely unlikely. So that's reassuring. And so a rough way to say this, when you're talking about sets, and after all, finite maps are a set of key value pairs. If you've got a strong hashes for the elements of a set, then XOR is a fine hash for the set itself. Okay. So there you go. We get n log squared n complexity by using this sort of structure var map decomposition, using ordinary hash conjugate for structures and pos trees, leaving the larger map alone when summarizing app nodes, and using XORs to hash var maps. So there's a couple of interesting and non-obvious ideas in this paper. It's a nice, for me, it's a nice use of computer science, right? Because we've actually had to, do some intellectual work and figuring out about the statistics of hashes and so forth to give an algorithm that is really noticeably better. And when I say noticeably better, here's we did, in theory, you can just say, well, it must be better because the math said it is, but we measured it as well. These are log plots, by the way. The left-hand graph is for synthetic balanced expressions, so balanced trees with lots of lambdas in them. You can see some arrows that give the slope of n squared and n and n log squared n lines, and the green circle is our algorithm, and it looks and low is good here. Low is good. So it looks as if we're bad because we're worse than De Bruyne and worse than structural. But you have to remember that De Bruyne and structural are both wrong. Right? That is, they give false positives and false negatives, and the false negatives mean that we will miss equalities, and we don't like that. So nevertheless, a useful baseline because they tell you something about the constant factor that we're paying in being worse than them. For the right-hand graph is for unbalanced expressions, and there you can see that locally nameless, which is a sort of version of De Bruyne that keeps locally De Bruyne, and for free variables it's non-De Bruyne. It's really the strongest competitor to what we described. It's described in the paper. Locally nameless is really very bad asymptotically, right? It goes quadratic on us, not good at all. We also tried some more realistic examples taken from machine learning setting, and we got similar looking results. So I mean, here's my conclusion that here's a problem that really ought to have a satisfying solution in the literature, but didn't, as far as I know. Must look up about code-De Bruyne indices, and here's an algorithm that seems to do reasonably well. And I would hope that this is a rather generic kind of problem. I'm sort of hopeful that this will at least form part of the menu of options for people seeking to do this kind of equality stuff in the future. So that's the talk, and I'm happy to take any more questions or observations, or indeed more general discussion about this or other matters.
Okay, let us thank the speaker first, then the questions. Hooray. I am aware of some potentially related work. There's a thing called authenticated data structures, which are not necessarily used for the same use case. Hold on, that is the title. And I'm just wondering if you've bumped into those.
No, I've never heard of authenticated data structures. A data structure whose operation can be carried out by an untrusted prover, the results of which a verifier can explicitly check as authentic. I'm sure I wouldn't have found that by randomly poking around, but now because it sounds like a different application area.
Yeah.
But I can see that there could be some connection, because in a way, the hashing is kind of like the thing that you check, maybe.
Yep. And sort of they would use hashes in a way to double check that a common sub-expression is the same sub-expression without revealing the contents of that.
Okay.
Sub-expression.
Cool. And then the thing that everybody's got to be somewhere. Oh, this is Conor McBride's stuff about but he uses code deploying. Okay, so I should go read this more carefully. Did we not? So I'm sure our paper refers to some stuff by Conor, but maybe not that. Yes. Okay. So at least we cite it. Yes. Okay, yes. So for what it's worth, I'll put in the chat a link to the paper. Let's see here, so you can see what I'm looking at, and what we've said in the paper about this work about Conor and so forth. The idea of representing a lambda with a map of the occurrences of its bound variables, which we adopt for our e-summaries, has been studied before, and that's sort of way back. Kenaway and Sleep describe another representation, director strings, in which implication about occurrences stored in the application nodes rather than the lambdas. McBride, that is his everybody's got to be somewhere paper, gives a very helpful overview of these approaches, but none of them addresses the question of compositional hashing. That's a pretty, what's the word, compact summary of related work. So I should probably be able to give a better story about that. Anything written by Conor McBride should be read by anybody interested in pretty much anything, actually. He said, anytime you're noodling around in related work and you see Conor's name, you should go and read his paper. So I did 9 months ago, I did read this paper, but I've forgotten it again, I'm afraid. So thank you for bringing it up again. And Christian, you pointed out the derivative of regular type is the type of its one-hole context. So yes, these paths are a bit like one-hole context.
Yeah.
No, they're like multi-hole contexts, actually, BOS trees.
I don't know where I read this. It was probably Conor McBride's thoughts as well, where there was an isomorphism between a path within a tree and I forget, sort of a string of something, letters in an alphabet. Can't remember exactly what it was.
Is this called like director strings?
Maybe.
Because there's quite old work by Kenaway and Sleep called director strings that connects up with work on combinatory logic, and and in fact it's described in my book, The Implementation of Functional Languages, my 1987 book. Golly, that's probably before some of you were born, but anyway, there's a whole chapter in there about combinatorial representations of functional programs, including this idea of director strings. And so that's yes, that's a representation of lambda terms that stores in application nodes a sort of a routing table that says where to send the bound variables.
Okay. That may be it. Is that sort of, I mean, when you talked about one keeping the flag of going left to right, and the fact that
Yes,
you have the position trees.
it's a bit
sort
like
of-
that. But the trouble with director strings is that it keeps in every application node a director, a way to direct every free variable. So it's inherently non-linear in the size
Yeah.
of the tree.
Yeah.
Whereas we just keep one bit in every app node.
Yeah.
Which side is the bigger map?
Sort of maybe somewhat related. Earlier you said that, so when you do bind a lambda, did you move the E structure underneath the lambda to say that this is the variable now bound? Yeah. In the present talk, I think.
Let's see. So
Way back when.
so here, so you mean when we go outside a lambda, inside the SLAM node,
Yeah,
S for
you now
structure
have a
lambda.
maybe pause tree, which
Yeah.
refers to the position. Yeah.
Yeah.
So now, what if you took the composition of two S applies, both of which contain the lambda?
Both of which contain that lambda, yes.
A lambda, yeah.
A lambda, yeah.
You could potentially replace a nested SAP constructor with the one SAP constructor where you've composed the lambdas inside.
No, you have to put an example in the chat.
So say apply F to G to X, yeah, where F and G both have a lambda associated with them.
F to G to X like this.
Yeah.
Okay, and then what?
And say you have a lambda function for both F and G that you're applying, right?
So they are both lambdas, or there's
Yeah.
a let binding for them.
Yep. And then you took the composition of those let bindings. Yeah, you'd obviously get the composition would also be a function. And then you'd have a single application node.
Wait, I'm applying lambda y dot blah to lambda z dot blah too. I'm not composing them.
Well, no, so say more in Haskell, and you'd have F applied to G applied to X. Say.
Yes.
Then that would be the same as F composed of G applied to X.
Okay.
Could you, in this system that you've described just here, take the composition of what F composed of G would mean, and then only have to deal with the one application node, right?
I don't get it. So I'm thinking this is just syntactic sugar for this.
Yes.
Okay, so now I've got a tree with I've got apply, which is presumably a constant, and compose that are constants.
Yeah, but presumably now the tree would be balanced differently, right? So if you've done some work figuring out what the composition of F and G are.
Oh, are you saying you could take a tree that's unbalanced and make it balanced as a sort of prepass?
Yes.
By applying enough built-in combinators somehow.
Yeah.
I hadn't thought of doing that. Maybe you could.
And then the question is whether you can still recompose the E structures and the hashes nicely.
Huh. I see. So you want to take a very unbalanced tree, like I suppose f of x and x1, f1. Here's a very unbalanced tree. F1 of x1 and f2 of x2, f3 of x3, f4 of x4, f100 of x100 and y. So, and you're going to somehow take that very unbalanced expression and you're going to give me a systematic transformation that will turn it into a much more balanced one. And then you'll do something on that.
Yes, hopefully.
Maybe, but you'd have to demonstrate it.
Yep.
And I don't know what that transformation would be.
Well, simply just precomposing the function, right? Because the way you wrote it, it would be, say, a very right-leaning tree.
Yeah.
And then if you composed F1 with F2, say.
Yeah, but I don't want to turn it into a very left-leaning tree. I've got to turn it into a balanced tree.
Yeah. Maybe you could reuse the depth information.
Maybe. Many things are possible.
Yep.
You should write a paper.
I should.
Yes, I hadn't thought of trying sort of rebalancing the tree as a first step, but that would be, suppose that would be.
Andrew also mentioned something about pause trees reminding him of zippers and contexts in reply to.
Yeah, Andrew, do you want to say more about that? That I mean, a pause tree it's not exactly like a zipper because it has these multiple holes. It's like a context with many holes.
Yes, my observation doesn't really go any further than that.
Yeah. But it may be because all of these things are kind of, they're kind of interconvertible with each other at some level. Though.
Yes. I think there's prior art in the area of generating some of these zippers automatically, or zipper-like structures. It may be extended to the positions trees as well, so that you don't have to redo some work that you would normally have to do for your core syntax data type.
Cool. Well, if any of you, because it's such a nice, tiny, well-characterized problem, if any of you feel inclined to noodle on it and come up with better solutions, that would be great.
We do have 10 minutes left. You did mention something about maybe opening up to more of the broader topic of Haskell.
I'm up for sort of ask me anything, really.
There's a question in the chat.
Thinking about formula, how would you approach enforcing that the set of paths in a hash file map both cover all of the variable sites in a given structure and do not include clashes? Oh, yes. Gale, is Gale the right way to pronounce your name? Yep, it is. Okay, so I don't know. It's certainly perfectly true that there are many combinations of hash maps and structures that make no sense. That's part of your point. So I don't know whether that matters really. I'd certainly not thought about how to carve out or characterize exactly the subset that do make sense, except by giving a function that called rebuild that fails outright. It's a partial function, just fails if it can't construct a sensible tree. Why would it, even if you could carve out exactly such a subset, why would that help? No, you're not. You've unmuted, but we still can't hear you. No, sadly, no sound from you. Oh well. Yeah. I do know about Andrew. Yes, I do know about Unison in principle, and it's a language that takes sort of equality of sort of source language subtrees very seriously. But I've never encountered it in practice, and I've never, surprisingly, perhaps surprisingly, I never talked to its author. So there might be some connection here, but I really don't know. I've got nothing substantive to say about it. Have you come across it in any depth? I mean, do you know if you used it or got any sense about it?
No, not really. I work with Haskell now, but I don't think it's very popular in academia. But I think the idea is very exciting of content addressed code.
Yeah.
It's just maybe a little too disruptive.
Yes, he tries to keep the to just have a sort of any sub expression is automatically sort of shared permanently. But what I'm not sure is, why is that a good idea? Is it because it reduces compilation time, or what's the goal? You remember?
Oh, they don't store source code in files. They store it in a append-only immutable database.
Yeah, and why
So
is that
it's,
an advantage?
Well, you don't have to type check it.
Right. So it reduces type checking time. Is that? I mean,
There's no type checking time at all. You send your code to the database once, and it stays there forever, and only only type checked code makes it into the database.
Yeah. So, but what's the problem with not doing that? Maybe that the type checker takes too long. So the goal is reduce type checking time. Is that right? Do you think?
I think there's more to it, because once you have immutable code and it's content addressable, I mean, Unison is kind of designed for distributed system setting.
Yeah.
So machines can ask other machines for pieces of code dynamically, rather than getting a binary first all at once.
Yes, that's true. And certainly if you're in a distributed setting, if you're trying to say, I want you to run this function for me on this data, then you've got to have some way to say this function. What do you mean by that? Well, one way to give is the name of the function, but that's not very good, because which version did you mean? So once you're into a distributed thing, then you need, yes, sort of canonical names for particular versions of particular bits of code. Yeah.
Yeah, exactly. Yeah.
Uh-huh. Application equality saturation. So Thomas asked whether I got plans to do anything with equality saturation. No, I don't personally. Equality saturation is when you make repeated transformations of the same program, perhaps hoping to optimize your program. So now at each step, you've got another program that's equal to the old one, and another one that's equal to the old one, and another one that's equal to the old one, and then and you can use this as a way to, as a sort of foundation for an optimizer. I've never had the experience of building an optimizer based on equality saturation, but I have talked to some of the people who do equality saturation. His remark was, oh, well, yes, what you're doing is indeed a little component of what we're doing, and next time we sort of are in that territory, we might think about using using your idea. So equality saturation is a whole bigger thing, if you like. I've forgotten the name of the guy. There's a particular group that has a really nice equality saturator called, I think, Egg, as far as I remember. I'm trying to find him. He'll probably, yes, Max Wilski and co. Yes, I think maybe that's him. This guy. Is he eGraphs good? Egg. Yes, that's right. Yeah, there you go. That's the one. So he certainly knows about the paper and liked it a lot. But I think we're not solving the same problem. It's more like that our stuff might be a useful component of theirs at some point.
Can you envision any use for things like Bloom filters, where you might have many algorithms for the hashing part?
Yeah, I suppose so. So why don't you summarize for everybody about Bloom filters and what they do for you?
So the point with Bloom filters is that you get a quick inclusion operation check, where for some amount of data you hash it with multiple hashing algorithms, and then you store those hashes basically. And with each additional algorithm, the probability of you getting sort of a false positive drops. So it's easy enough to check whether an item belongs to a set by just checking whether you've had enough of the hashings of that item stored.
What was, you have multiple filters, and if they all say yes, the chances of it being wrong are pretty low.
Yeah.
Yeah. Still non-zero. I mean, if you really cared about you still might want to do that final check. So maybe you
Mhm.
could use, instead of a single hash function as I've described, you could have multiple hash functions that were a lot smaller, or produced a lot smaller hash codes.
Yeah.
Each of which effectively is a kind of Bloom filter.
Yeah.
Yeah.
But presumably, so you've mentioned something about having shown in the paper that XOR is strong enough in this case, even though it's not a cryptographic hash function.
Yeah.
Then I imagine sort of the same argument would mean that you don't necessarily need multiple hash algorithms to do this.
Yeah, I think our story here would be that one hash algorithm is good enough, provided it's got enough bits, that it will distribute the expression pretty well across the space.
Yeah.
So then if you've got one that does that well, then having multiple is not obviously better than just having the same one with more bits.
Yeah. Is there any reason why you might use something like a non-lossy hash function, say, for example, where you take the prime numbers as bases, and then you...
I don't know. Yeah, non-lossy hash functions. You'd have to be...
if you think about it, it will be effectively a compression scheme rather than a hash function.
Exactly, yes. And you'd have to be sure, you'd want to be sure that it really was going to be a compressor, right? Not an expander.
Yeah.
So there's a paper called Every Bit Matters.
Okay.
Which is quite a nice take on, it was about serialization for typed lambda terms. Nice paper by Andrew Kennedy and his colleagues here at Microsoft Research. I forget if we cited it, but
in a sense, because you always look at which subtree is smaller, that sort of seems to me a bit like what do you want to call it? Sorry, the most trivial of compression algorithms. I'm drawing a blank. Where you use the frequency of the alphabet to basically reorder.
Oh, Huffman encoding or
yes.
something. Yeah. Yeah. That's right. Maybe there's a sort of weak connection there. Yes. Yeah.
All right.
Yeah.
Well, we're technically out of time, but if anybody still has any thoughts or ideas, please feel free. If not,
Great. Well, an hour and a half is usually saturation time for the Zoom calls anyway.
Well, in that case, we'll thank our speaker again,
Yeah.
and hope to see you all tomorrow at 10 a.m. local time.
Great. Okay. It's been my pleasure. Thank you.
Thank you so much.
Hope you've enjoyed yourselves and have a good time. Do good PhDs and stuff. Okay.
Thanks.
Thanks then. Bye.
Bye.
Bye.